Imagine this is a comet from another star system drifting through the cold outer reaches of our solar system suddenly begins to leak water even though it's almost 3 times farther from the Sun than Earth. No comet should behave like that. And yet in early 2025, astronomers witnessed exactly that, a small icy traveler breaking all the rules of space science. From the start, 3I Atlas looked like a typical comet. But when scientists began to study it closely, they saw clear signs of water escaping from its surface. The rate of water loss was extremely high, estimated at around 40 kilograms every second. That is a massive amount of vapor for a comet located almost 3 times farther from the Sun than Earth. At that distance, sunlight is too weak to heat a comet enough for its ice to turn into gas. Most comets in our solar system remain almost inactive that far out. This made 3I Atlas unique. It was doing something that ordinary comets cannot. This discovery is important for 2 main reasons. It shows that water, one of the most basic ingredients for life, exists in other planetary systems, and it gives scientists new insight into how material survives the journey between stars. For the first time, astronomers have detected the chemical signature of water from an interstellar comet. After its discovery by the Atlas telescope, 3I Atlas quickly became the focus of major space observatories. Teams using NASA's Hubble Space Telescope, the James Webb Space Telescope, and several ground-based instruments began collecting data almost immediately. But the key evidence that proved 3I Atlas was leaking water came from a combination of ultraviolet and infrared observations. When sunlight strikes a comet, it causes ices on the surface to warm up and release gas. That gas spreads outward to form a glowing cloud called a coma. By studying the wavelengths of light coming from that coma, astronomers can identify which molecules are present. In this case, the signal that caught everyone's attention was from hydroxyl, a molecule that forms when ultraviolet light breaks water apart. Whenever hydroxyl is detected around a comet, it's a clear sign that water is escaping from its surface. NASA's Neil Gehrels Swift Observatory, designed to observe ultraviolet light, was one of the first to spot that hydroxyl emission coming from 3I Atlas. The Swift data showed a sharp, repeating pattern that could only be explained if the comet was continuously releasing water vapor into space. Meanwhile, the James Webb Space Telescope observed the comet in the infrared spectrum, which allowed scientists to directly see the signatures of water ice, carbon dioxide, and carbon monoxide. JWST's sensitive instruments confirmed that the water signal was real and that it was increasing as the comet approached the Sun. The researchers also used the Gemini South Telescope in Chile to capture high-resolution images of the comet's coma. In those images, the dust appeared to be shaped by jets of gas erupting from the nucleus. These jets are thought to be produced when buried pockets of ice suddenly heat up and burst through the surface, throwing out both vapor and solid grains. When all of these measurements were compared, the data lined up perfectly. The emission from hydroxyl detected by Swift, the infrared spectrum captured by JWST, and the visible light images from Gemini all described the same phenomenon: water being released from an interstellar comet at an incredible rate. To make sure the results were accurate, astronomers ran computer models to simulate how 3I Atlas would behave if it contained various types of ice. The best match occurred when they assumed that the comet's core was made mostly of water ice mixed with small amounts of carbon-based materials. This combination could explain the observed outgassing without requiring exotic chemicals or artificial processes. But one question remained. At its distance from the Sun, 3I Atlas should not have been warm enough for normal water ice to sublimate. So what was really causing it to leak water in such large quantities? This puzzle led scientists to the next phase of research, understanding the mechanism behind the leak. To understand why 3I Atlas is leaking water so far from the Sun, we first need to look at what happens to a comet's ice in space. Normally, a comet remains frozen while it travels through the outer solar system. The Sun is too distant for its rays to heat the surface enough for ice to turn into gas. That process, known as sublimation, usually begins when a comet moves inside the orbit of Jupiter. But 3I Atlas is behaving differently. It is already releasing water even though it is nearly 3 times farther from the Sun than Earth. At that range, the temperature should be around -150 degrees Celsius. Regular water ice cannot sublimate easily at such a low temperature. This means another mechanism must be driving the leak. Scientists think that 3I Atlas contains a special type of supervolatile ice. Supervolatiles are materials like carbon monoxide and carbon dioxide that can vaporize even in extreme cold. As they warm slightly, they create pressure beneath the comet's surface. That pressure can crack the outer crust and open small vents. When that happens, trapped pockets of water, ice are suddenly exposed to sunlight and start to escape. This theory explains why astronomers have seen both water and carbon-based gases coming from the comet at the same time. The supervolatiles act like a trigger setting off bursts of water vapor. Each eruption launches dust and gas into space, forming the bright halo around the nucleus that telescopes can detect. Another factor that may contribute is the comet's rotation. Observations suggest that 3I Atlas spins roughly once every 16 hours. That steady rotation means different areas of the surface are constantly moving in and out of sunlight. Every time a region warms up, it could begin to vent gas. When it rotates back into shadow, the vent freezes again. This on-off cycle can create the pattern of periodic outbursts seen by telescopes. There is also the possibility that the comet's structure is extremely porous. If the nucleus is full of tiny voids, then heat can penetrate deeper than expected. In this case, even weak sunlight might be enough to warm subsurface ice. As the vapor rises through the porous layers, it can carry dust grains with it. That would explain the faint jets visible in images taken by the Gemini South telescope. Laboratory simulations on Earth support this idea. When researchers create artificial comet samples using water ice mixed with carbon monoxide, they find that gas pressure inside the sample can become strong enough to break the crust. The escaping gas drags bits of ice and dust into the vacuum, just like a miniature version of what we see on 3I Atlas. All of this evidence points toward a natural explanation. The comet is leaking water because of internal heating and supervolatile reactions, not because of any artificial or alien source. The process shows how complex and dynamic icy bodies can be even in the cold darkness between stars. The presence of water also tells us something about the comet's origin. Water ice forms only under specific temperature conditions. If 3I Atlas carries large amounts of it, that means it was born in a region of its home star system similar to our outer solar system where temperatures stay low enough for ice to survive. That discovery connects our solar system to others in a very direct way. The same chemistry that shaped our comets appears to exist in distant systems as well. It reminds us that the building blocks of planets and possibly of life are not unique to us. In most cases, comets that come from other star systems look and act very differently from the ones that orbit our Sun. The first interstellar object ever discovered, 1I Oumuamua, showed no clear signs of gas or dust at all. It looked more like a dry fragment of rock or metal than a typical comet. When scientists saw 3I Borisov in 2019, it finally showed a true comet-like tail, but even then the rate of water loss was small. Atlas is the first interstellar comet to show such strong and active water emission. That makes it a unique opportunity for scientists to study how ices behave when exposed to new conditions. Its level of activity seems to be much higher than expected for an object so far from the Sun. The amount of water released each second could fill an Olympic-sized swimming pool every few minutes. The discovery challenges old assumptions about how interstellar comets evolve. Until now, most models suggested that after millions of years of traveling through deep space, the surface of such an object would become inert. Radiation from cosmic rays should turn the outer layers dark and crusty, sealing the ice beneath. But 3I Atlas shows that even after long exposure to interstellar conditions, some comets can still react strongly to sunlight. One explanation may be that the comet is geologically young on its outer layers. Perhaps it was ejected from its home system only recently and has not had time to build a thick crust. If that is true, then we are witnessing a piece of another planetary system in a very fresh state, a fragment that still behaves as it did when it first formed. Another possibility is that the comet's surface is covered by a thin layer of dust that cannot trap heat effectively. This would allow solar radiation to reach deeper pockets of ice and trigger eruptions. In either case, the result is the same: water being lost into the vacuum at a surprising rate. Astronomers are also intrigued by the composition of the escaping material. Spectroscopic analysis suggests that the water from 3I Atlas contains a ratio of deuterium to hydrogen similar to that found in comets from our own solar system. This is an important clue. It suggests that the chemical environments where comets form may be similar throughout the galaxy. The same basic processes of ice condensation and dust accumulation might happen around many young stars. The isotopic fingerprints also help scientists compare potential origins. If the ratio of heavy water in 3I Atlas matches what we see in our solar system, that means our local neighborhood is not special in its chemistry. It could also mean that the ingredients needed to create oceans and maybe life itself are widely distributed among the stars. I Atlas therefore acts as a messenger from another world. It carries information not in words but in molecules and minerals. By studying it, we learn not only about a single comet, but about the environments where planets and organic compounds might emerge elsewhere. This is one reason why astronomers are watching it so closely. Every observation adds one more piece to the puzzle of how materials move between star systems. Each particle of water escaping from the comet is a clue about temperature, pressure, and composition in a place we can never visit directly. And yet the object remains temporary. Like all comets, it is losing mass every time it approaches a star. Over thousands of years, it will shrink, fragment, and fade back into the darkness of interstellar space. That makes the current opportunity especially precious. For the scientific community, this event marks another step in understanding the cosmic exchange of matter. It shows that star systems are not isolated. They share materials through comets that wander between them. Water which once froze around a distant sun can now be detected by our telescopes billions of kilometers away. The discovery of water leaking from 3I Atlas is not just about a single comet. It opens a window into the chemistry of entire star systems. For decades, astronomers have asked a deep question: are the materials that built Earth common across the galaxy, or are we a rare exception? Every interstellar object that passes through our solar system gives us one more chance to test that question. When water is detected in a comet, it tells scientists that hydrogen and oxygen came together under cold conditions. Those are the same conditions that existed in the early solar system when our own comets and icy moons were forming. The fact that a comet from another star system behaves in such a familiar way means that the same processes might be happening everywhere. If water ice can form in distant protoplanetary disks, then so can other compounds such as methane, ammonia, and carbon dioxide. These are the molecules that act as the first steps toward organic chemistry. It suggests that the ingredients for life could be spread throughout the galaxy, carried by countless icy comets like 3I Atlas drifting between the stars. Scientists studying astrobiology often look for three main requirements for life: liquid water, a source of energy, and organic molecules. Finding water from an interstellar comet checks one of those boxes right away. The next step will be to see if carbon-based molecules are also present in its tail. Instruments on several observatories are searching for these signals, but they are faint and difficult to detect. If those molecules are found, it would mean that even in the frozen depths between stars, chemical reactions can create complex compounds. That would strengthen the idea that life's raw ingredients are universal, not limited to one corner of the cosmos. This idea is both thrilling and humbling. It means that our solar system is not an island. Instead, it is part of a larger galactic network of dust, gas, and ice that constantly exchanges material. Comets like 3I Atlas act as the delivery ships of that network, moving essential elements from one region to another. From a technical point of view, This discovery also shows how advanced our observation tools have become. The Swift Observatory was originally built to study high-energy bursts from distant galaxies. Yet its sensitive ultraviolet detectors could also identify the faint signature of hydroxyl fragments around 3I Atlas. This ability to adapt instruments for new purposes is one of the quiet strengths of modern astronomy. It also highlights the importance of cooperation between space agencies. Observatories from NASA and the European Space Agency are working together to track 3I Atlas as it continues its journey. Each telescope collects data in a different wavelength of light, building a complete picture of the comet's behavior. Future missions like ESA's JUICE spacecraft on its way to Jupiter may also get a brief chance to observe the comet from a unique angle. When that data returns, it could confirm whether the water comes mainly from the surface or from floating fragments of ice. Such information will help refine models of how comets behave when they enter a new solar environment. The measurements of water loss from 3I Atlas are among the most accurate ever made for an interstellar object. By comparing the rate of gas release with the amount of dust visible in images, astronomers can estimate the comet's size and density. The numbers suggest it is a few hundred meters across with a low mass and a fluffy porous structure. That structure is typical of comets that formed slowly in the cold outer regions of a protoplanetary disk. It implies that the same slow process of ice and dust sticking together occurs in other star systems as well. In a sense, comets are fossils of planet formation. Studying them tells us about the early stages of building worlds. The discovery of 3I Atlas therefore connects several fields of science at once. It involves physics to understand how the ice turns into gas. It uses chemistry to identify the composition of that gas. And it reaches into biology when scientists ask what this means for life elsewhere. Each discipline adds one more layer to the story. Perhaps the most inspiring idea is that somewhere, around another star, a planet might be forming. From the same kind of material now escaping from 3I Atlas, water, that once froze on this tiny traveler could be raining on an alien world millions of years from now. It reminds us that the universe is always recycling its ingredients. Nothing truly goes to waste. Even as the comet speeds away from the sun, it continues to teach us. Every observation deepens our understanding of how connected the galaxy really is. What began as a simple detection of ultraviolet light has become a window into the shared chemistry of the cosmos. I Atlas will not stay near the sun for long. Its orbit is open, which means it entered our solar system from interstellar space and will soon leave it again forever. Every day it moves millions of kilometers farther away, growing dimmer as it escapes the warmth that caused its water to boil into vapor. Within a few months, it will be too faint for most telescopes to see, but the data it left behind will keep scientists busy for years. Astronomers are preparing to combine observations from several observatories to create a complete model of its behavior. By comparing the water production rate at different times, they can estimate how the comet's surface changed as it traveled closer to and farther from the sun. They will look for signs of fragmentation to see if pieces actually broke off to form smaller ice chunks as the main body rotated. The European Space Agency's JUICE spacecraft, which is on its way to explore Jupiter's icy moons, will also point its instruments toward the region where 3I Atlas travels. It may detect ultraviolet traces of the same hydroxyl light that first revealed the comet's secret. The results of that observation will probably reach Earth in early 2026 and could offer the most detailed look yet at this interstellar visitor. Other missions, such as the James Webb Space Telescope and future ultraviolet satellites, will keep watching for similar objects. Each new discovery helps improve search algorithms so that astronomers can detect interstellar comets sooner and study them in more detail before they fade. What makes 3I Atlas special is not just its water. It is what that water represents. It proves that even across the vast distances between stars, the basic chemistry of life can survive and travel. Hydrogen, oxygen, carbon, and nitrogen are among the most common elements in the universe, and comets act as the vehicles that mix them across star systems. Long ago, similar comets may have delivered water and organic material to the young Earth. Now we see that the same process could be happening everywhere. In that sense, 3I Atlas is a messenger showing that the building blocks of life are not limited to one planet or one star, but are woven into the fabric of the cosmos itself. When we detect that faint ultraviolet glow from a distant comet, we are not just seeing light. We are seeing a connection across space and time. We are witnessing atoms that once formed near another sun, now interacting with the light of ours. Every photon tells us that the universe recycles its materials over and over, creating endless chances for planets and possibly life to emerge. Even though 3I Atlas will soon disappear, it leaves behind a legacy of questions. How many more interstellar comets are passing through unnoticed? Could some of them carry more complex molecules? And will we one day intercept one directly with a spacecraft to sample its materials up close? Plans for such missions already exist. Engineers are designing fast interception probes that could launch within days of a new discovery. These spacecraft would travel at enormous speed to meet an incoming interstellar comet, take samples and return them to Earth. The data from 3I Atlas helps define what instruments such missions will need. In the bigger picture, discoveries like this change how we think about our place in the galaxy. For a long time, scientists treated star systems as separate bubbles, each with its own planets and comets. But now we know that objects move between them. Material that forms around one star can later drift through interstellar space and eventually visit another. The galaxy is not a collection of isolated systems. It is a connected web of matter where nothing stays still forever. When you think about it that way, the leaking water from 3I Atlas is not just a random event. It is part of a continuous cycle that may stretch back billions of years. Ice forms around a young star, freezes into a comet, gets ejected into interstellar space, and later melts again near another star. It is a story of movement and transformation written across the galaxy. In the coming years, telescopes will search for more of these visitors. Each one will bring a new piece of information about how planets form and how materials move between stars. And maybe one day we will find a comet that carries even more direct evidence of organic compounds, the seeds of life drifting between systems. Until then, 3I Atlas remains one of the most fascinating messengers we have ever encountered. It reminds us that the universe is not static or empty, but alive with motion, chemistry, and change. Every drop of water escaping from its surface adds to the grand story of cosmic evolution. The next time you look up at the night sky and see a faint streak of light, remember that it could be a traveler from another star releasing its secrets as it passes by. Somewhere out there, another world may be watching one of our own comets and wondering the same thing. That is the beauty of discoveries like this. They connect us not only to the science of the universe, but to its mystery. 3I Atlas leaking water in space is more than a scientific fact. It is a sign that even across the cold emptiness of the galaxy, the ingredients for life continue to flow from one world to another, waiting for their next home.